Hello! At this year's PLDI, I would like to present a new parsing algorithm for all context-free languages. On the surface, it is based similarly to those proposed by Maid and recently by Henriksen on computing the derivatives of the grammar by successive input symbols. However, we represent these derivatives in a different way. Our representation is immutable, acyclic, and very often factorizable, which enables a novel, very effective technique of memoizing parser steps. Our algorithm matches the best-known theoretical complexity bounds and beats current implementations of other generalized parsers on practical inputs by a few times when constructing parse forests and by dozens of times in recognition mode. See you at PLDI.
Hi, my name is Romain Edelman. Jadamza, Victor Kunchak, and myself are excited to present the parsing algorithm for LL1 context-free expressions based on derivatives and zippers. Context-free expressions are a combinator-based formalism for describing relations between token sequences and user-defined values. LL1 context-free expressions are a subclass of those expressions where all ambiguities can be resolved using a single token of lookahead. The derivative of an expression by a token is another expression, which encodes the state of the original expression after processing that token. We present a technique based on zippers to compute the derivative of LL1 expressions in amortized constant time, leading to a novel linear time parsing algorithm. We present an implementation of the algorithm as part of Scallion, an open source scalar parsing combinators library with state-of-the-art performance. Additionally, we have formally proven the approach correct in Coq. We look forward to seeing you at our presentation.
Modern software is often compiled with optimizations, and we often want to debug the optimized program. For example, in GCC, we can use the G flag to generate the debug information. However, is the generated debug information always correct? Unfortunately, the answer is no, because compiler optimizations may affect debug information generation. Let's see an example. In this program, if the debugger stops at the return statement and prints the value of I, the output should be 0. But if we compile it using GCC 8 with O3 optimization and use GDB to print the value, we get 1, which is incorrect. This is a problem related to the debug information. We designed a systematic testing framework for debug information validation. Surprisingly, even mature compilers have problems in this aspect. If you want to know more, please come to our talk.
Hello, I'm Jimmy Couple. Today I'm presenting Yogo, our new semantic code search tool. Imagine searching for every instance of some concept in a codebase, like this one-dimensional bounce check. Even this simple example is hard to search for, as instances may take many forms, such as with nested if statements. With Yogo, the user writes a single declarative query. From this, Yogo's equational reasoning engine will be able to find nearly any instance of this concept in the code, almost regardless of form, even if it's in a different programming language. For more information, check out our new PLDI paper, Semantic Code Search via Equational Reasoning.